Alright, so I wanted to show you a practice problem just in this video where we go through and we look at how the pH changes as we add a strong base to a weak acid and do a full titration problem with you so that you could use that. So let's say that we have a weak acid, HA, and we don't need to name a real acid, but we are titrating this with NaOH, so OH minus, and we're going to form A minus and H2O. And let's just say, so that we can, deal with this problem in a reasonable amount of time, that we have 30 milliliters of the acid and it has a 0.1 molar concentration. And let's say that we're titrating this with 0.1 molar OH minus. And we're going to keep titrating this until we reach the equivalence point and go beyond. So the first thing that we can calculate for this is when the equivalence point will be reached. And we can do that by doing MAVA equals MBVB. And since there's no normality here because they both have one H and one OH, we can just leave it like this. Sometimes we might have to do times number of H plus and times number of OH minus to account for that, but we don't have to in this case. So now when we go through and do this, we see that we have 0.1 molar of the acid and 30 milliliters. And for the base, we have 0.1 molar. And so the volume of the base that's going to be needed to neutralize this would be 30 milliliters. Now you'll also be given the Ka of the acid. So the Ka of the acid, let's say, is 1 times 10 to the negative fifth. And so now you'll be asked to go through and calculate things. Like, for example, they could ask you, well, what's the pH when 0 milliliters of OH minus are added? And when we try and do this calculation, all that we're doing is just having the acid in water. We haven't added any base to it. And so we're going to have A minus, and we're going to have H3O plus. And so this really isn't even a titration question. It's before we started titrating. And so for this one, we would have, x squared over 0.1 equals 1 times 10 to the negative fifth. When we solve for x, we would get 1 times 10 to the negative 3, and we would get a pH equal to 3. And this would be, a straight-up equilibrium problem. You could write out an ice table for it, but I've done that many times. I'm going to save time here and not do that. So now, what happens when we add some base to this? So let's say that in our next step here, we decide to add 15 milliliters of OH minus. So now we started with 30 milliliters of HA and 0.1 molar of it. Something I like to do is, instead of changing this to liters to save time, I just leave it as milliliters. And so that would actually give us, instead of moles, we would get something called millimoles, which are a little bit easier to work with because the numbers aren't as small. So that would just be 0.1 times 30, so that would be 3 millimoles. And let's say that I added my 15 milliliters of my OH minus, which also is 0.1 molar. And so that value would give me 1.5 millimoles of OH minus. Well, now, using my reaction up here, if I cut and paste this, no, that's not what I wanted to do. I didn't want to cut, I wanted to copy and paste it. So if I take this and I copy and paste it down here, well, now I'm going to have my moles of each one. I'm going to react them. And this is like the problem I did in the last video. 3 millimoles, 1.5 millimoles, and 0, minus 1.5, minus 1.5, because the OH is limiting, plus 1.5, and in the end I have 1.5 of HA, and I have 1.5 of A minus. And so now what you need to realize that you have a buffer. pH is equal to the pKa. The pKa is going to be this 10 to the negative fifth value. We're going to take the negative log, so that's 5, plus the log of A minus, which is 1.5 over 1.5. Notice I don't even bother changing it back to molarity here. You don't have to. The ratio is what's important. So here's my buffer problem, and in this case, this is going to just be 1. So my pH is going to be 5 here. And we're right in the middle of the buffer zone in the titration curve. Well, what happens if I keep adding base until I get to the point where I have 30 milliliters? So now again, let's cut and paste this reaction right here. I'm just going to take that 0 with it. That's fine. And let's say that I've now at this point have a situation where I have 30 milliliters. So let's change to a different color just to differentiate here. So let's say that I have 30 milliliters of our acid with the 0.1 molar, and now I've added 30 milliliters of my base, my 0.1 molar base. Well, now we know from the first part where we figured out how much base you would have to reach the equivalence point that we're at the equivalence point. And so we have 3 millimoles of each one and 0 of the A minus. So now they're going to completely react. -3, -3, +3. And at this point here, now we don't have any of these left, and we have 3 millimoles of our A minus. Now my A minus, it's a weak base. It came from a weak acid, and because of that, it will actually react with water, and it will form an equilibrium with water. And when we do that, when we show it forming an equilibrium with water, it's going to look like this. So here we go, just in case we need more room. Our A minus is going to form an equilibrium with water. It's going to react with the water. It's going to undergo something called a hydrolysis, where it breaks the water apart into OH minus, and we're going to form HA. It's essentially the reverse of this reaction up here if you're confused about how do I write that. It's the reverse of that reaction. Now the A minus, again, the A minus is the conjugate base of HA. So remember, Ka times Kb equals Kw. Kw is 10 to the negative 14th. In this case, Ka is 10 to the negative 5th. Kb we don't know, but we're going to find it out. It's 10 to the negative 9th. Now, with a K expression, we can set up an ice table here, but we need to be in molarity. It won't work in millimoles. So we need to take this millimole here and divide it by the total volume. The total volume was 60, 30, and 30. So it's going to be 60 milliliters. Notice how I can still work in milliliters because I was in millimoles, saving myself some time. 3 divided by 60 is 0.05 molar. 0.05 molar of A minus, 0 and 0, minus X plus X plus X, X, 0.05 minus X. But we can neglect this minus X here, so we're going to have X squared over 0.05 equals 10 to the negative 9th. And now we can solve. Now we can solve for X. So we can times this by e negative 9, and then we can take the square root of that, and we would get that X is equal to 7.1 times 10 to the negative 6. That is my OH minus. I can then take the negative log of that, and I would get the POH, which is 5.15. I can then subtract that from 14, and I would get 8.8. So now I have my pH as 8.8. What would be a good indicator to use? Go check out the chart. Tell me what indicator would be good to use, but phenolphthalein would work nice for this, and it would do a good job because the change is between 8 and 10. Now, our curve, we could keep going here and do one more calculation. What if I were to add, if I had my HA, I wonder if this will still paste. Yeah, awesome. If I had my HA with the same amount, so I had my 30 milliliters and my 0.1 molar, and I had my now 40 milliliters. Now we're past the equivalence point. Now I'd have 3 millimoles, I'd have 4 millimoles, Now I would be subtracting the limiting acid. The acid has already run out. Now notice I don't care about A minus at this point because I have 1 millimole excess of OH minus. This is what decides my pH. If I divide this by the total volume, 70, then let's see what we get here. We have 1 divided by 70. So that would give us 0.014 molar OH minus. If I do the negative log of that, I would get 1.84. If I subtract that from 14, I would get 12.15 or 12.16. This would be my pH. Look back at the curve. Let's take a second and look back at this curve. Here's my curve. I started off with a pH that was around 3. I had a buffer zone with a halfway point around 5. I had an equivalence point that was higher than 7 because of that A minus. And then when I added some extra, I was up here around 12. This is what a curve looks like. These problems are what you see on the AP exam. They're involved like this. Again, very quickly, just to recap here before I stop, we start off with a situation in which there is going to be, they're going to ask you maybe how much base you needed to add to neutralize the acid. We figured that out right up here. We'll highlight in pink. They then might ask you, well, what's the pH of the acid when 0 milliliters of base are added? And we do a straight up Ka problem. We then have a problem where we've added some base, but not all of the base. And then we have something that's in the buffer zone, and we get a pH that is around 5. This is when we've gone about halfway. Then we have the last calculation where you have equal amounts, where you're at the equivalence point. And in this case, this requires the most work. You have to take the moles of A minus, divide it by the total volume to get the new concentration that you write in a new reaction, a hydrolysis reaction. You also have to keep account of the fact that A minus has a Kb, and you have to find that Kb using the Kw equation. You then have to set up an ice table and plug in and solve for x. The x only gives you OH minus though, so once you find the POH, you then have to find the pH. And finally, they could go past the equivalence point in which you have excess OH minus. You have to change that to molarity, do the negative log, and then 14 minus it to find the pH. This is the hardest type of question that you'll see in acid-base, where you have these 4 steps. Thanks for watching. Hope that was helpful.